Hi, everybody. Okay, we are going to be starting Unit 6 today. These are going to be our notes over Day 6.1. Day 6.1 is all about direct variation, inverse variation, joint variation, and combination variation. Now, you've probably seen direct variation because you did in Algebra 1. Depending on who you may have had for Algebra 1, they may have kind of introduced inverse variation as well. But if not, no worries. That's what we're here to talk about today. We're going to talk about, we're going to add on inverse variation, like I said, joint variation, and combination variation. Like I said, just to give you a little background, this is originally a group activity, but since we are all chilling at our houses today, group activities are just not possible. So I have turned that group activity into a quick little PowerPoint. Now, if at any time you feel that this PowerPoint is going too fast, or you're like, oh my gosh, can this lady please slow down? Not a problem. That's why you have a pause button. So if you feel like it's going too fast and you need to get caught up, just hit pause, and when you're ready to go, pick it back up. So let's go ahead and get started. All right. So, not gonna lie, guys, like that little transition of the curtain opening. Hopefully, all these transitions will make all the different transitions from slide to slide will make it just even a little bit more fun for you. But anyways, so this slide right here is talking about, is the data direct variation, inverse variation, or neither? Okay, so we have some tests, but before we get to those tests, we need to define some variables. So you know how we have independent and dependent variables. So just going forward, we're going to let X stand for the independent variable. We're going to let Y be the dependent variable. And if you remember back from your Algebra 1 days, Y depends on whatever X is. So since Y depends on X, Y is the dependent and X is the independent variable. So, and then we're also going to introduce possibly to some of you a new variable, and that's K. We're going to let K be the constant of variation. So when we're talking about variation, we're going to let K stand for that constant. So that's going to be the variable you'll see a lot throughout this entire presentation. So the first test that we're going to do is, first of all, you're going to look at your X and Y on your data. Okay, if X and Y are both increasing at the same time, so in other words, as X increases, Y is increasing, but it also could be they're both decreasing. So if X is decreasing as Y is decreasing. Okay, so the main thing here is that they both have to be doing the same thing. They both have to be increasing, or they both have to be decreasing. If that is occurring, then what we're going to do next is we are going to check to make sure they all have the same constant of variation. So if we see, oh, they're both increasing, or oh, they're both decreasing, then we're going to look and we're going to perform this little test where it says K equals Y over X. So we're going to take each Y, put it over its respective X, and find out what the simplified value is. If they produce the same value, so each Y over its respective X, if that produces the same value, which is our K, for every point on the data table, then we're going to say that this represents direct variation. Now, if they're doing opposite, so if X is increasing as Y is decreasing, or X is decreasing as Y is increasing, so if they're doing opposite things, then we're going to look and say, okay, their constant of variation. So if they're doing opposite things, we're going to take and we're going to multiply X times its respective Y. So if X times its respective Y for each point on that data table equals the same value, then we're going to say that that data represents inverse variation. Okay? So just to reiterate, if X and Y are both decreasing or both increasing, and they produce the same value when I put Y over X, it's direct variation. If X is increasing as Y is decreasing, or X is decreasing as Y is increasing, and when I multiply the X times the Y, If that gives me the same value, then it's inverse variation. And obviously, if neither situation fits, then we're just going to say the data is neither direct or inverse variation. So if it doesn't fit either test, it's just neither. It's not direct, it's not inverse. All right? Now, let's look at our first example. So we have a data table here, and they want us to determine is it direct variation or inverse variation and why, and then they want us to find the constant of variation. So I look at my x's, and my x's are all decreasing because it goes 4, 3, 2, 1. And I look at my y's, and my y's are all decreasing 12, 9, 6, and 3. So they're both doing the same thing at the same time. As x is decreasing, y is decreasing. So since they're doing the same thing, I'm going to check and see, do they have the same constant of variation? Do they have that same k value? Okay, so first thing is we've noticed that they're doing the same thing. They're both decreasing. So then I'm like, okay, which k is it? Okay, if they're both doing the same thing, then that is k equals y over x. Okay, so we're now going to check if y over x produces the same value for each ordered pair. So I'm going to take first, and I'm going to put 12 over 4. Well, 12 over 4 simplifies to be 3. Okay, but we got to check it for every point on the data table. Now, here's the thing. You can't just stop and go, oh, well, the next one produces the same value. It's this. No, because guys, what happens is it may work for the first two, but you may get to that last one and he doesn't work. And so if you don't test every data point on the table, you're not performing a true test. And again, we could sneak one in. Hey, the first 1, 2, or 3, they all produce the same value, but you get to that last one and it doesn't. And yes, we would trick you like that because we want you. It's not a trick, but we're trying to get you to see that you've got to test every data point. So, continuing on, my next y is 9, and its x is 3. So 9 over 3 is 3. Then I test 6 over 2. That's 3. And then lastly, 3 over 1, 3. Okay, awesome. So they're both doing the same thing in terms of increasing or decreasing. They're both decreasing. And when I do y over x, because I'm feeling like it might be direct variation, so I'm going to do y over x. Since the y over the x is the same, then we can say it is direct variation. So this is direct variation because x and y are decreasing, and the y over x produces the same value of 3 for each ordered pair. So direct variation. And then we get, of course, part B said, well, what is that constant of variation? That constant of variation is the same simplified value that each y over x produced. All right, let's look at example 3. I apologize, that's example 2. Okay, I've been at home way too long already. So it's example 2. Same idea. Is it direct or inverse in y? And then find the constant of variation. So I'm looking here. Okay, so my x's are increasing. 3, 4, 5, 6. And then I'll look at my y's. Well, my y's, as the x's are increasing, the y's are increasing as well. Because it goes 1.5, then 2, 2.5, and 3. Okay, so I'm thinking it might be direct variation. But just because I have a pattern of x is increasing, y is increasing, I still have to see if will they produce the same constant of variation. So if I'm thinking it's going to be direct, then that means I have to use y over x. So I'm going to take, and remember, you've got to test every data point on the table. So I am going to do my first y over x, which is 1.5 over 3. And 1.5 over 3, well, that's 1/2, because 1.5 is half of 3. Okay, I'm going to try the next value, which is 2 over 4. Well, 2 over 4, that reduces to 1/2. So we're good there. The next data point is 2.5 over 5. Well, 2.5 is half of 5, so that's 1/2. And lastly, 3 over 6, 1/2. Well, luckily, they all produce the same value. Now, if at any point you had gotten one that you're like, the first one worked, but the second one didn't, then you can stop. But if you keep getting yeses, like, yes, that produces the same value, that produces the same value, then you've got to test each data point. Okay, but lucky for us, they all produce the same value. So since they're both increasing, since both x and y are increasing, and then when I do y over x, I get the same value, that means it's direct variation. Okay, now part B says, what's the constant of variation? Well, we don't have to do any more work. We've already found it. It's 1/2. So our k value is 1/2. Now we're at example 3. So, same situation, different data table. So, I'm looking at x and y, and okay, the x's are increasing, but the y's are decreasing. So, x is going up, 1, 2, 3, 4, but y is going down, 24, 12, 8, 6, like that. So, I'm thinking, since I have using what I've learned on the previous slides, okay, if they're doing opposite things, then it might be inverse variation. Okay, so I'm thinking it might be inverse, but I don't know for sure, because for it to be inverse variation, yes, they have to be doing opposite things, like one's increasing, one's decreasing. But in addition to that, we also have to make sure that x times y, because it's inverse. So we have to make sure that x times y produces the same value. Okay, so for my first one, I'm going to do 1 times 24. And I get 24. For my next one, I'm going to do 2 times 12. That's 24. Then I'm going to do 3 times 8. That's 24. Then I'm going to do 4 times 6. That's also 24. So excellent. X and y are not, they're not doing the same thing, they're doing opposites. So x is increasing, y is decreasing. Okay, so they're doing opposite things, and x times y produces the same value k for each ordered pair. So it passed both tests, so therefore I can claim it's inverse variation, because both x is increasing and y is decreasing, and x, y is 24 for each ordered pair. So that means, since it equals 24, that is our constant of variation. All right. So next slide. So we know how to find the k. We know how to determine, is it direct or is it inverse. Now let's take that one step further and let's see how we can find the model equation. So I have kind of a little flow chart for you. If it says that x and y vary directly, then you're going to use the direct variation side of the flow chart. So the first thing you have to do is, typically they'll give you an ordered pair and they'll say that x and y vary directly. And so the first thing you always need to find is that k value. You need to find that constant variation. So since it's direct variation, we're going to use the k equals y over x. We're going to find k. Then once we find k, we're going to substitute the k we just found into the equation y equals kx. But since we're writing the equation, we want to leave x and y as variables. Okay? So your first step is to find the k and then use that k in the equation, because y equals kx is the equation for direct variation. Now, if we tell you that x and y vary inversely, they vary inversely. Same first step. You've still got to find the k, but we're going to use a different equation to find k. We're going to use k equals x times y. Okay, so If it's inverse, your k is x times y. Then once you get that k, you're going to substitute the k you just found into the equation, y equals k over x. And we're going to leave x and y as variables. So regardless of which one it is, direct or inverse, that first step when you're writing the model equation is you've got to find the k. Then once you find the k, then you can sub it into the respective equation, leaving x and y as variables. All right, so let's jump into some examples. Example 4, it says 1/2, 3 is a coordinate from a direct variation. Okay, so 1/2, 3 is the coordinate from a direct variation. So we're going to find two things. We're going to find the constant variation, then we're going to write the model equation. Okay, since this is direct variation, we're going to use the k y over x. So I take the y they give me and I put it over x. So that gives me 3 over 1/2. Now, remember, this is an integer or a value being divided by a fraction. So you probably want to, since you've got a fraction in the denominator, you probably want to turn this around and write it as 3 divided by 1/2. Now, remember what we talked about when we were talking about fractions. Dividing fractions, don't ask why. We're going to flip the second and multiply. So that becomes, instead of 3 divided by 1/2, it's now 3 times 2 over 1. 3 times 2 over 1 is 6. So we found our k value. It is 6. Okay? Now we've got our k value, so we can turn around and write the model equation. Since this is direct variation, we're going to use y equals k times x. And to write the equation, remember, we leave y and x as variables. We just sub in that k value we found. So that's y equals 6x. And that's the model equation. Not too bad, right? Told you this was going to be easy. All right, let's try another one. So we have example 5 here. It says x equals -3/10 when y equals 2/9, and they vary inversely. So, same instructions as the last slide. They want us to find the constant of variation and then find the equation. So, since they vary inversely, that means inverse variation, we're going to use that formula to get the k value. So k equals x times y since it's inverse variation. So I'm going to multiply -3/10 times 2/9. Now, if you're thinking, well, dude, that 3 will cancel out with the 9 and change that to a 3. You're right, and you can do that. You can cross cancel, and then 2 goes into 10, and you can, like I said, cross cancel and cross reduce, all that stuff. But if you're like, what? Then it's totally okay to just multiply the fractions. Multiply the tops, and then multiply the bottoms. And by doing that, you get -6 over 90. Well, 6 goes into 90 15 times. So that becomes -1 over 15. All right. We've got our k value. So once we've got our k value, we just have to substitute that into the model equation form. So since it's inverse variation, we're going to use y equals k over x. So when you first write it, it looks like this, where we have a fraction in our numerator. And while that's easy to determine our k value, it's not exactly the best way we can write that, okay? Because we don't like fractions within fractions. We want to completely simplify those down. So, if you remember kind of from what we did above, that's like -115 times 1 over x. Because remember, dividing fractions, don't ask why. Flip the second and multiply. So, flipping the second, or in this case, the denominator, x over 1 becomes 1 over x. So now we can multiply the tops, multiply the bottoms again, and we're with y equals -1 over 15x. So while that -1 over 15 over x is it's not incorrect. It's just the most correct or more correct when it's simplified and you don't have a fraction within a fraction. But here's one thing you want to remember. Just because 15 is in the denominator doesn't mean it's not still part of the k value. So if I gave you an equation, y equals negative 1 over 15x, and I said, hey, what's the k value? You know that 15 is going to be part of it. So you can just kind of peel it away and know that it's negative 1 over 15 is your k value. So don't think just because it goes to the denominator that it's no longer part of the k value. It still is. It's just this is a prettier way to write it, if you will. All right. Last example for this one. This one's a little bit different, though. Example 6 is just a tad. It threw in another piece of the puzzle here. It says each pair of values is from a direct variation. Find the missing value. So it gives me two coordinate points, 318 and x comma 27. Now, that looks a little odd because when we write coordinate points, we normally have a value where that should be. So this means after we get that model equation, we're going to have to do one more step to find out what x is. So steps 1 and 2 where you get the k, and then step 2 where you write the equation, those haven't changed. We're still going to use 318 to get our k value and write the model equation. But after we write the model equation, then we're going to have to plug in the value from that second coordinate to help us find out what x is. So here we got to find k. So now you're like, well, okay, how do I know which one to pick? Okay, you want to pick the coordinate value that has values for both x and y. Okay, always pick the coordinate point that has both x and y, because you can't do anything if you don't. Okay, so we're going to use 318, and since it's direct variation, we're going to use the k that is y over x because it's direct variation. So I did 18 over 3 and I found out k was 6. Woohoo! We got k. Now we're ready to write our model equation. And since it's direct variation, that's y equals x. So that means since my k is 6, it's y equals 6x. All right, we're good, but we're not quite done yet. Okay, so cool. I've got, since they're from the same direct variation equation, I've got the equation. So what I can do now is plug in the y value and then just solve for x. All right. So I get 27 equals 6x. Well, you know we got to solve that. So we got to divide by 6. Now, remember, you're not going to have a calculator on this. Okay? So you can't give me a decimal. And besides, I wouldn't want you to give me a decimal because something over 6 is irrational. It's one of those never-ending decimals. So we just reduce it. They both reduce by 3, and I get 9 halves. So x equals 9 halves. Really not anything that much more difficult, but it's just an extra step. So if they give you 2 points and one of those points has an unknown, find your k, write the model equation, and then use the known quantity from the second point, plug it in, and solve for the missing variable. Now, there's also another approach. So you can do the approach we did before, but I'm going to show you another way. So we both know that they're from direct variation, from the same direct variation. So what if I set them up and found the k for both both points? Now I know you're probably going, what? You can't do it. Well, we kind of can. It's just one part's going to be a variable. So I'm going to find the k value for both points, just like we did in example 4, example 5, and the previous example 6. So for the first point, I'm going to, again, direct variation, y over x, 18 over 3. Now, instead of changing this to a plain Jane integer 6, I'm going to leave it as a fraction. You're going to see why here in just a minute. But if you're doing this approach, you want to make sure you leave both cases fractions. You'll thank me for it later. All right, so let's do k for the second point. So y over x. Now, I only have y in this case. I don't have x. So I'm just going to have to leave that 27 over x. Now, if they're from the same direct variation equation, the k value should be the same. They're supposed to be the same, or else they're not from the same variation. So, using the fact that they both equal k, I can set them equal. Got it? They both equal k, therefore they equal each other. Little weird flashback from geometry, the transitive property. Remember that? If a equals b and b equals c, then a equals c. So that's all we're going to really employ. But if you think about it, they both equal k. They're both from the same direct variation. Therefore, they equal each other. So we're going to set both of those equal. I'm going to set 6 over 1 equal to 27 over x. Now, this is why I told you to leave it as a fraction and not write it as a simple 6, okay? Because now you're going to cross multiply. So I get 6x equals 27. I divide by 6. I'm back at 27 over 6, which reduces still to 9 halves. So it doesn't matter which way you do it. So if you look at the first version of example 6, we found k, we found the equation, we plugged in the known quantity, solved for the unknown. The second approach, I form the k from both points. So I do k for both points, and then I set them equal. Now, it doesn't matter to me which method you use. It really doesn't. They're both mathematically accurate and mathematically legal. So you pick the approach that works for you, and I'm happy. Okay, let's talk combined variation now. Combined variation. This is the slide where we're going to talk about combined variation and joint variation, because really, joint variation is kind of a subset of combined variation. So, how can we write the combined variation model? If it says y equals, then you're going to see y varies. So varies, if you think about it, like when we're talking word problems and we were writing equations from word problems, anytime we saw the word is, that meant equals. Well, in this case, anytime you see the word varies, that means equals. So it's going to be y equals if it says y varies. If it says z varies, then it's going to be z equals. So whatever comes before the word varies is on the left side of the equal sign. Whatever comes after the word varies, that's going to be on the right. So varies, in this case, think of it like meaning equal. Y varies, y equals. Z varies, z equals. Okay? And of course, it doesn't have to be just x, y, or z. You can use your dependent variable of choice. Okay, it depends on whatever word problem you're doing. Yeah, I know. I think I just heard y'all all groan from the other side of this video. Word problems, but they're really not that bad. I promise. The main thing is once you get the equation set up, you're golden. So that's what we're talking about here. So, varies equals y varies, y equals, z varies, z equals. Okay. You're going to put the k, which remember is your constant of variation. You're going to put that k value in the numerator. K is always going to go in the numerator. Okay? And I know you're like, wait a minute, we just put that 15 in the denominator. Yeah, we did. But remember what I told you, that 15 is still part of the k value. So he's just like hanging out in the denominator. But if we were to pull that k out, he would go back to the numerator. Okay? So you'll always put k in the numerator. Okay? Here's another big one. You're gonna write variables that represent direct variation. Those go in the numerator. So if something varies directly as, whatever comes after directly as, that goes in the numerator. So direct variation goes in the numerator. Where do you think inverse variation is going to go? Inverse variation is going to go in the denominator. Because think back to the equations. If it's direct variation, it's k times x. X is in the numerator. But if it's inverse variation, then x is in the denominator. Remember, that is k over x. So inverse variation is k over x. X is in the denominator. So direct variation in the numerator. Inverse variation, denominator. Now here's where the joint variation comes into play. Joint variation means to multiply multiple things in the numerator. So guys, joint variation is just a big old fancy direct variation. So if it says, y varies jointly as x and z, then that's going to be x times z in the numerator. So think of joint variation, it's just a big old fancy direct variation. Joint variation is going to be in the numerator. Okay? Also, one big thing, and this is huge, and I see people make mistakes over this every year. So really pay attention. That's why it's red, underlined, all that good fancy stuff. When describing a combined variation, or even just a direct variation or inverse variation, the k is never part of the description. Okay? K is never, you're never going to say it varies as 2/3 or whatever. No, you're never going to see combined in any kind of variation. You're never going to see the K in the description. You're going to have to find the K, so it's obviously not going to be in the description. Okay, so don't forget when you're writing the combined variation, don't forget to always put it in the numerator, because we're not going to tell you what it is. We're going to make you find it. All right, let's go with example 7 here. It says, and this one is a practice, and then we'll do 2 more, okay? Then this is going to be a combined variation problem, because as you can see, we've got like 3 variables floating around here in this problem. So it says the number of bags of grass seed, which we will refer to as N. N represents the number of bags needed to reseed a yard, varies directly with the area A, so A represents the area to be seeded, and inversely with the weight W of a bag of seed. So let's try to read that again. The number of bags N varies directly with the area A and inversely with the weight W of a bag of seed. Now, here's where we're going to get our data points from. It takes 2 3-pound bags to seed an area of 3,600 square feet. How many 3-pound bags will seed 9,000 square feet? Okay, so when you're tackling a problem like this, the first thing, always, you cannot pass go, you cannot get $200, you have to do this step. The first thing you always do is you write the variation. And that comes from where we threw all those variables out at you. Okay, so we're going to write the equation model. The number N represents numbers. Now, if you get past all the reseed yard, blah, 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 okay, N varies directly. Well, N varies, N equals directly with A. So since it varies directly with A is in the numerator. And inversely, that means we put this one in the denominator, inversely with W. Okay, N varies, N equals direct with A, so A in the numerator, inversely, that means denominator, with the weight W. Now, again, we're not going to give you K, so as soon as you write out where A and W go, you better smack that K up in the numerator. Because if you don't, you'll forget it and your whole problem's going to be like, what? Okay? It'll be wrong too. So that's sad. But, okay, so we go to the next step. It takes 2 3-pound bags, area 3,600 square feet. So it takes 2 bags. 2 is in. 2 bags. N is the number of bags. 3 pounds. That's the weight of your bag. So that's going to be in the denominator for W. And area, that's A, 3,600 square feet. So you sub in the given data. You want to take the part of the problem that has all 3 variables represented. 2, that's N. W is 3, that's weight. A is 3,600 because that's area. And now I've subbed in this data, and now I just have to solve for K. Now, you could do one of 2 things. You could multiply by 3 on both sides to get rid of that division by 3 and divide by 3,600. Or, in this case, 3,600 is divisible by 3. That becomes 1,200. Either way, perfectly fine. So, like I said, either way. Now, on this one, what I did is I multiplied both sides by 3. But, again, here you could do 3,600 divided by 3 is 1,200. It really doesn't matter. Again, it does not matter which way you tackle this problem. But I chose to multiply both sides by 3 to get rid of that division. So, I got 6 equals 3,600K. I divide by 3,600. Now, 6 goes into 3,600, 1 over 600 times. Okay? So, 6 over 3,600 simplifies to be 1 over 600. Now, we're going to write the model equation. We're going to use K to write the model equation. So, that means I take K, I sub it in, but I leave N, A, and W as variables. Now, and on the other one, I told you go ahead and that would become 1 over 600W. If you're doing a word problem like this, you don't have to mess with that. Okay? You don't have to flip the second and multiply and all that stuff. You don't have to do that because this model equation is a means to an end. Now, if I said just write the model equation, then yeah, you'd want to clean that up and simplify it. But since we're going to go further and we're using it to find an unknown, you don't actually have to clean it up and make it all pretty. Okay? So, it wants to know how many 3-pound bags will seat an area of 9,000 square feet. So it wants to know N because it wants how many. The weight is still 3, and the area, the A, is 9,000. So now that I've got my model equation, I plug in the known quantities. I know W is going to be 3, and I know A is going to be 9,000. So now is when I get to clean it up. So you probably want to do some scratch work off to the side. 1 over 600 times 9,000. You'd simplify that, and then you'd divide that value by 3 or multiply by 1/3, either way. And when you clean that up, you get 5 bags. So like I said, what I did, and I just didn't show it, but what I did is I did 1 over 600 times 9,000. I cleaned that up and then divided that quantity by 3. So you might have some fraction work to do off to the side. All right, so we know that we're going to need 5 bags to seed 9,000 square feet. Now, let's get into some more practice problems. Example 8. Let's read the problem. That always helps. The time T needed to complete a task varies inversely as the number of people P. It takes 5 hours for 7 men to install a new roof. How long does it take for 10 men to complete the job? So, first step. Again, always always your first step, you've got to write that equation. So time varies inversely as the number of people. So time varies. That means t equals, and since it's inversely, the people are going to go in the denominator. Now again, we're not going to tell you what k is, so you've got to put the k in the numerator. Doesn't matter if it's inverse, combination, direct, joint, k will always go in the numerator. So time varies, t equals, inversely, that means denominator, people. So p is in the denominator. So we've got our model equation. Now we're going to go to the next sentence. It takes 5 hours for 7 men to install a new roof. So 5 is going to go in for time, because hours are time. And 7 men, those are people. Okay, so I'm going to plug in 5 and 7 to find k. So 5 goes in for t, 7 goes in for people. Now, how do you undivide by 7? You multiply by 7. So you solve for k, and I get that k is 35. Okay, so really nothing new here. We've got our k. Now we're going to take our k, and we're going to plug it back into our model equation. And I get t is equal to 35 over p. Yay, we've got the model equation, but we're not quite done. It then goes on to say, well, how long does it take 10 men to complete the job? So if I add 3 more guys to your roofing install, then how long is it going to take them to complete it? So this time, I want to know how long. So I want to know t. So I'm going to leave t as a variable, but I'm going to put 10 in for the number of people. And I get 35 over 10. Now, I'm going to do 35 divided by 10, and I get 3.5. Because, guys, we have to think about this in terms of real world. If you own a roofing company, you're not going to tell your person it takes 9 over 2 hours, 9 halves hours. You're not going to tell them that. You're going to say, oh, it's going to take 4.5 hours, or it's going to take 2.3 hours. So you have to think in realistic terms here. So if you get a word problem, again, we're not going to want you to say, hey, it takes 7/3 of an hour. And they're going to go, what? They're going to want you to say, oh, it's going to take like 2.3 hours. Okay, that's it. So again, think in terms of the real world on these application problems. Now, last example, example 9. So this one, now it's not a word problem necessarily, it's just a combination variation. So it is okay to leave things as fractions here, because it's not a word problem. So it says, but the steps are the same, guys. The steps are the same regardless of if it's a word problem or just a plain old simple plain Jane math problem. All right, so it says z varies directly with x and inversely with y. When x equals 6 and y equals 2, z equals 15. So I want us to find z when x equals 4 and y equals 8. So first step, again, always, write that equation. So z varies, that's going to be z equals directly with x, x is going in the numerator, and inversely, that's denominator, y. So that's going to be our first step. Write that model equation. So z varies, like I'm showing you here, z equals directly is x, x is in the numerator, inversely with y, y is in the denominator. And again, you've got to put that k value in the numerator. Just got to put a k there, because that's your constant of variation. And we're not going to tell you what it is, we're going to require you to find it. Okay. So now it tells me the values for x, y, and z. So I've got to find k. Finding k is always the second step. I plug in 15 for z, 6 for x, 2 for y, and now I simplify. So in this case, I did 6 divided by 2. You could multiply by 2 and then divide by 6, you're going to get the same answer. But here I just did 6 divided by 2. So I got 3k equals 15. Divide by 3, you get k is 5. Awesome! Now we can write our equation. So I just 7k and I leave x, y, and z as variables. This is our model equation. Now that we've got the model equation, I go back up and it says find z when x is 4 and y is 8. So I plug in the known quantities and solve for the unknown. So my k, that stays 5, my x is 4, and my y is 8. So I'm solving for z. So 5 times 4 is 20, and I get 20 over 8. Now, these reduce by 4 each. So that gives me 5 over 2, 5 halves. Now, because 5 over 2 is a pretty decimal, okay, because it's a pretty decimal, you can turn it into a decimal if you'd like. As long as we don't say, hey, round to this or leave as a fraction, if it's a pretty decimal, you can tell me 5 over 2 or you can tell me 2.5. All right, so this brings us to the end of our lesson. All right, guys, please know from the bottom of our hearts, we all miss you guys. And we're ready to be back at school. But we have to take care of each other, and we have to also be careful that if we're a carrier of coronavirus, that we're not around people who could possibly contract it from us, because you might not have symptoms, but you're still a carrier, or you still have the virus, and you could pass it on to somebody else. So again, practice social distancing. And I know it's tough, guys. I'm right there with you. For my kids that are watching this video, you know that I'm right there with you. I am an extrovert 110%, and I like being around people, and this is tough for me too, guys. Okay, I haven't seen my family in like a week, but that's okay, because I have the immune system issues. I don't want to be carrier and pass it on to my parents and all that good stuff, okay? Like I said also too, I don't have an immune system, so I don't want to come into contact with somebody that has it. So I know the pain, I know the struggle is real, y'all. But you've got Snapchat, you've got Instagram, you got iPhones, you got FaceTime. So practice social distancing. If we do that, this thing will be over quicker than it would be if we didn't. All right, wash those hands, stay healthy, stay inside. Like I said, just take care of yourselves, because guys, even after it's all said and done, the math is going to be here, but you got to take care of your health first, okay? So take care of yourself, be safe, make good decisions, and the quicker we can all get back to school, the quicker we all can to see our friends and see all you guys. So, like I said, just be good, make good decisions, miss you, we will see you back. Feel free to drop us emails. You know, if you're not in my class, drop your Algebra 2 teacher an email, okay? Let them know you're okay. Let them know what you did over spring break. Same for my kids. You want to drop me an email? That's awesome. I would love to hear from you guys. So, anyways, I hope everybody is enjoying their extended spring break, and we will talk again soon. Your homework for this lesson is homework 6.1. Okay, you'll also notice when you, at least on my Canvas, when you open up the homework, I have the homework key attached. So you're able to check your answers and see if you're getting the right answer. And then we'll, if we haven't already talked to you about how to turn in your homework, that will be coming soon. But like I said, just take care of yourselves and be safe out there, guys. We all want to see you back in school when we're able to come back. All right, take care. Have a great one. We'll talk to you soon. Bye, guys.